Hi, so I thought I'll do a second video of these. This time, I want to show you how you can essentially set up a local large language model that allows you to do things like image classification, as well as text, interactions or text classification in a way that's very similar to what you would do with, for example, the OpenAI API, except that everything that you do is local, which means no data gets sent to sort of a platform provider such as OpenAI or Anthropic or any of the other AI providers. API providers. This has the following advantage that, of course, your data remains private. And in particular, if you're working with secure data, confidential data, it might be important to make sure that data is not being shared or that you kind of work in a closed ecosystem. In some work that I do with national statistics authorities or sort of supporting researchers in national statistics authorities, this is where sort of the frontier innovation now is, because of course, national statistics authorities have access to very confidential information, and so it's very important that they do not, use that data in an environment where it's not entirely clear whether such data might leak. And so working with a closed local AI installation allows you to do a lot of great things very efficiently, very simple. So let me just show you how this goes. Share my screen. Here we go. So the solution that I want to show you is called llamafile. It was developed by the Mozilla Foundation, which some of you might now know. Mozilla used to be a sort of a web browser that has now a big sort of open source foundation, has been a strong supporter of open source. One of the challenges with inference, which is what you actually do when you chat with a large language model, is that in order to do inference efficiently, the large language model, needs to be loaded in memory, and the inference is done typically more efficiently via a graphics processing unit because the architecture of a GPU, a a regular processor on a machine, is much more adapt to the neural network that is ultimately what a large language model is. And so many solutions that allow you to run a local, large language model locally actually do not leverage the fact that many of our computers actually have a GPU unit to deploy the large language model on, but rather they leverage the computational capacity of the simple processor. And this is inherently less efficient than working with a GPU. And so it can take minutes and minutes to answer a prompt on a local installation that leverages CPU when it can sort of be very quick seconds if you actually are able to leverage the GPU. This is what llamafile allows you to do. Llamafile recognizes on your system whether you have a GPU that's amenable to deploy the large language model in to do inference. And so it can make the inference task much faster. And as I said, has all the other benefits. It's coded very close to the machine core, so to say. It's coded in C, and it basically turns any large language model. And there's a set of ones that you can work with. We have Lava 1.5, Tiny Llama, Mistral 7B. We have various coding, sort of various LLMs that have been trained on a large corpus of code to actually, work quite efficiently and quite effectively, providing you an interface almost as if you were running on almost as if you were interacting with the OpenAI visual chat interface or with the API, which is what some of you might be doing if you interact with it programmatically. So how does it work? Again, it's Very simple, so there's nothing much to do. I'm working here on a Mac device that has a decent GPU to work with. So the instructions, I mean, for the case of Llama or Lava, is very simple. You just download it, you open the terminal, you make sure that you convert the Llama file into an executable, which means that you can run it. And then, you execute it. And I'll show you a quick then application of how you can use this, for example, for a conversation around image classification. Let's dive into it. So, you download the Llama file. This takes a bit of a time because it's, well, it's a 4 GB file. And today my internet is a bit slow, but I've already downloaded it. The next step is you move into the terminal and you turn your data set, which right now it just looks at a file, you allow that to be executed. And this is what you can do with the change mod command that says, well, the plus X means allow it to execute. It's like running it as if it is a program. So when we, oops, I'm in the wrong directory. When we move into the download folders, which is where the file is stored, we can now make this file executable, and then we can simply launch it. And actually, the launch sequence is quite interesting. So just observe what it says here. Oh, it has recognized that it has an Apple M3 Max as, and I'll jump back, has an Apple M3 Max as a processor, but it also recognizes it recognizes the GPU. And so it adapts, so to say, it's executable in a way that it leverages the fact that we have a decent GPU here on this phone, on this device. And what you see is, there's things about buffer size and whatnot in terms of the executable. It then launches a server, which is essentially a local version of the website that you have when you go to ChatGTP, for example. Um, and here in the background, it sort of like then lists sort of the interactions with the machine. So let me just show you this. So this has launched now the browser window because this is essentially the website that allows you to interact with that executable. And so we can, perform a simple chat. Can you write me a haiku, which is, a Japanese sort of short poem. And it does its task. And as you've seen, it was very fast in terms of the execution. In the background, what it does, it actually, again, let's just do this in parallel. So let's go start with the main. Just show you this in parallel just to help you understand sort of what is going on behind the scenes, so to say. When I initiate this request, so I click send here, you will see that in the terminal window, there's some action going on, which is sort of saying, the web interface is communicating via the API with this large language model, and then sort of, presents the output in this form. So in terms of the visual interface, it gives you actually a lot more options than what you might be used to when working with OpenAI or ChatGTP. For example, here, you can actually set a lot of parameters that with a visual interface with ChatGTP, you wouldn't be allowed to set, or you can't set. Only if you have access or work with the API, you can have some scope to navigate this. There's a lot to get into, but ultimately, you can sort of determine like the length of a prediction sequence, the number of tokens. You can also essentially affect how noisy the prediction will be, the inference will be. In the inference step, what the LLM is doing, it simply navigates, it samples based on the prompt, it maps your prompts into what is called embeddings, and it sort of then tries within a neural network find a good location within the neural network as to where your prompt fits that has been mapped into that vector space. And then essentially, you just move along that network. And of course, in the movement along the network, some neurons are connected within the neural network with a certain probability. Um, and as you might know, like the large language model can hallucinate. It means, it sort of samples from that sort of network that it seeks for information to answer your prompt. So it gets propagated through the network. And so, the length of the prediction is something that, is a parameter, but also, the amount of noise that you allow, the temperature that you allow it to make jumps in the inference step between branches of the network that might be more or less strong connected in the training data, in the data that the large language model has been trained on. This is obviously a very simplified characterization, um, but this is in essence sort of what's going on. Let me so here, if you read up a little bit on neural networks, you will see that you can figure out essentially a lot in terms of the tuning. That tuning these parameters is very important, and you might want to tune these parameters in a way that allows the large language model to perform in a way that is consistent with what it is that you want to get out of the interaction with the large language model. Let me now show you how you can embed that into a pipeline or sort of a process interacting with that local large language model with data such as image data that you might not have worked with in the past for simple image classification tasks. So this is, again, not that difficult, but for those of you who are not familiar with coding with Python, again, the cost of learning how to code with Python has gone down a lot, again, thanks to lots of LLMs that allow you to actually turn a prompt into code and a code back into text, basically. And so here is an example. This is essentially a function that sends, a request to the local large language model, to the API that we can see is visible here, in terms of documenting the interaction. And actually, the language and the format of this follows very much the format that, if you've done this before, you might be familiar with the OpenAI API. So we have the URL of the endpoint, which in this case would be, your local installation. So it would be 1.27.0.0.1.1 or local host. I mean, that these two things are the same thing. So this is a local internet address, so to say. It's locally hosted. And you have an API key, which you actually don't need here because it's your own model, so to say, your local model. You have to specify the specific model that you're working with. In this case, it's Lava 1.4 that is operating on that endpoint, and the payload. The payload would typically be, a chat interaction that has been converted into JSON format for the interaction. So let's have a look at what this does. I mean, this is all a very standard function. Here we have the URL endpoint. We're using the completion endpoint, not the chat endpoint. Again, there's no key. The model is this Mistral. And what I'm doing in this exercise is I'm going to ask it to describe, so this is something else. I'm going to ask him to describe this image, which is me with my dad in a sort of local newspaper report around the green transition when we looked at the installation of a ground source heat pump. So it loads that image. It turns it into an encoding that the large language model can work with. So it's basically ultimately, it's turning the image into text. And it's sort of code, so to say. So it encodes the image into text. And then the payload, if the base image, that conversion has been successful, the payload is very simple. We have the model that we have to give it. we give as the user that is interacting with the model the following prompt: describe the image and what you see. The image here is referred to as image 12. And then we're waiting for the assistant to respond. The assistant is the LLM. And the image data here is specified as that base64 image object, which again is just a variable reference, which we gave the ID 12. So here, this would ensure that we transfer the image data, and we're telling the large language model that this is an image that the assistant is supposed to classify or engage with. And we extract a response after leveraging this function of that sends the interaction, that just sends the payload to the large language model. So let's do this. Let's run this. As you can see, it's relatively fast. So this is just the content of the sending of the payload. That here I'm putting that out. As you can see, I'm just printing the payload just for you to debug or understand or make it visible. The image gets sent. This whole thing took 5 seconds to execute. It's actually much faster in terms of the actual classification text. This is not particularly precise. As you can see, there's 3 men standing in a garage posing for a photo. The men are standing close to each other, with one man on the left of the side of the group, another man in the middle, and a third man on the right. They appear to enjoying their time together, possibly in a workshop or a garage setting. So you can see that this is not super precise, but this is how you've established, or how you can establish, a pipeline. And of course, you can set in the call to the large language model, you can play around, you can tune the parameters. If you have a sufficiently large training set, you can tune the parameters to sort of give more or less conservative answers. Again, I can illustrate this here. So let's reset this to default. And the image classification task is very simple. You can also interact with it here in that interface. So what is the advantage here? You can essentially perform a simple image classification task or image retrieval of data from images on your local device. You can refine the prompt further to make sure that the LLM gives you structured output. So rather than as we see here, it gave a free text response, we can actually ask it to give a structured output, such as a JSON object itself, saying, count the number of humans that you see in this picture, count the number of men that you see in this picture, and through that. You can then sort of, for example, retrieve large-scale information from a large corpus or large database of images, turn that into tabular format, and perform analysis on this. And as I said, the crucial difference is no data leaves your device; it actually remains on your local machine. And that allows you to obviously work with confidential data that you might be, not super happy if that were floating about in the internet, which we do think we know is happening. If you think around, your images that you upload on Facebook, at some point it was quite evident that Meta was using these images to work with and develop tools such as these type of image classification models or other forms of data. Google has used this quite extensively for its CAPTCHAs. Its CAPTCHAs were helping actually train some of the AI that goes into the operations of the autonomous vehicles. In case you didn't know that, but I think it's pretty obvious how often you had to pick on, is this a traffic sign? Is this not a traffic sign? Is this a traffic light or not? Anyways, this is a nice illustration of the capabilities here. And as you can see, it's very easy to essentially do an exercise that allows you to work with a large language model locally. It's very versatile. You can, as I said here, the grammar's argument here is the bit that allows you to specify a JSON scheme for the response in case you're looking for structured responses. And as I said, you can play around with many tuning parameters. You should read up a little bit on these to essentially work and deploy a large language model locally at scale at basically zero cost in a very efficient way. I hope this was helpful.